Okay, got cut off there because I have the free version of Screencastify, so we're halfway through this question. Anyways, so we said that it's not going to be 18A because that'll make it shift to the left. So let's take a look at 18B. Is sulfide going to be reacting with PB? So let's take a look. So here is sulfide right here. Does it react with PB? Yes, it does. It's going to be forming low solubility. So what if you added NaS? What's going to do? It's going to react with PB, lowering it, and that'll make it shift to the right. Okay, I'm going to skip over C for a second, but if we added PbNO3, what that would do is PbNO3 NO3 is just soluble with everything, so Pb would increase this concentration right here and make it shift to the left right here. But Na is soluble with everything, NO3 is soluble with everything, it's not going to form precipitate, and so this would have no effect on this reaction right here. Okay, which equation has the KSP expression of this thing right here? So we have aluminum sulfate. We have to have the coefficients of 2 in front of the aluminum and the coefficient of 3 in front of the sulfate. So I just look for it. 2 in front of the aluminum, 3 in front of the sulfate. We have aluminum sulfate. That's our answer right there. Okay. Now, moving on. What is the KSP for zinc hydroxide if it has a solubility of 1.3 times 10 to the minus 7? So here's zinc hydroxide. Big 2 right there. OH minuses right there. Okay. As zinc hydroxide is put into solution, it's going to dissolve into a X to 2X ratio. Okay. Now, the KSP of this thing is going to be zinc times hydroxide, like that, squared, right? That. Or in other words, KSP in this case is going to be X to 2X squared, or KSP equals X times 2X times 2X. 2 times 2 is 4. X times X times X is X cubed, 4X cubed. Okay, so what is X? It's 1.3 times 10 to the minus 7. So go 1.3 times 10 to the minus 7, cube it, and then times it by 4. Okay, you do have to follow your order operation, so don't times it by 4 first. So I'm going to go, 1.3 times 10 to the minus 7, cube button, and then times it by 4. And I get 8.788 times 10 to the minus 21, or 8.8. Close enough. Okay. Which compound will have, number 21, which compound will have the lowest solubility? Okay. Again, I think earlier we said silver nitrate is soluble. Everything with nitrate is soluble. So that's not going to be the lowest. Let's take a look at silver bromate. Silver bromate is times 10 to the minus 5. So something times 10 to the minus 5. Okay. Strontium sulfate. Strontium sulfate is times 10 to the minus 7. I'm just kind of like ignoring the first number because and we'd have to look at the first number if they both had the same scientific notation coming after it. But I have a feeling usually they don't. Strontium carbonate is times 10 to the minus 10. Okay, since this one right here is our smallest number, it's going to have the lowest solubility. So that's that one. And then second would be strontium sulfate, and then silver bromate, and then silver nitrate has high solubility. Number 22, the definition of a Bronsted-Lowry acid should contain which of the following? So Bronsted-Lowry acids are donate hydrogen ions. So it's just a definition question, okay? This one's just wrong, and this one's just wrong too. The acceptance of a hydrogen ion or a proton is a base. So yeah. Which equation represents the reaction of a Bronsted-Lowry base with water? So this is a kind of a funny question, and it's kind of worded a little bit funny. Well, it's not worded funny, but maybe worded a little bit tricky. So if we have a Bronsted-Lowry base with water, water is acting as the acid. Okay, so that means water, just like the previous question we just did, water is donating or giving up one of its hydrogens. So if we had water and it gives up one of its hydrogens, it loses one of its hydrogens, it's going to turn to OH minus. Which one of these things has an OH minus in there? That one right there. I just want to double check to make sure that we didn't mess something up. So it's a reaction with water. This one, under the definition of a Bronsted-Lowry base, should be accepting a proton or a hydrogen ion. And so it goes from N2H5, it takes a hydrogen on and turns into N2H5. Sorry, it goes from N2H4 and turns into N2H5. So yeah, that's my answer right there. Oops. Okay, number 24. Which is the strongest acid? Okay, first is we should probably identify the two acids right here. Again, looking for something that is losing a hydrogen. So H2BO3 turning into H3BO4. Nope, this one's going to be a base. As it turns into this one right here, it's going to be accepting one. But in the reverse direction, H3BO3 is going to be a losing one, so that makes this one an acid. And by default, that makes this one an acid as well. But just to double check, H2PO4 loses an H and turns into HPO4. So what are my strongest acids? Well, these are my only two choices. Okay. So it's either going to be this one, or it's going to be this one right here. So now we just need to go to the table and compare it. So we're looking for H3BO3 and H2PO4. And we have to look at it on the acid side. Here's H3BO3 and H2PO4. So they're right beside each other. But H2PO4 is stronger because it's higher up. It has a higher Ka value. So H2PO4 is the stronger of those two. So H2PO4 is the stronger of those two right there. Which species will result in a solution with the greatest hydronium concentration? That means the strongest acid. And these are all bases, actually. There's not even one of them has a H in there. But so since these are all bases, if we find the weakest base, that'll have the greatest amount of acid in it, or have the greatest amount of hydronium. So you may have seen this kind of picture before. Here's like the pH scale. So here's like pH 7, and here's like pH like 14, and then here's like pH 0-ish. Now, since they're all bases, they're all going to be, so in other words, pH 7 has equal parts of hydrogen and equal parts of OH minus. Okay, so 50, 50, right? Now, these are all bases, so we're looking for the base that is furthest, that is the weakest. So like something like right here-ish has a little bit of hydrogen. Obviously, it's going to have more OH minus, something like that. And some of these bases are going to be probably a little bit on the stronger side, like way up here. So what we're trying to do is we're finding the weakest base, okay? So CnPO4, CO3, C2O4. CnCO3, PO4, C2O4. Oh, okay. Pretty clear winner right there. So the strength of our base is at the bottom. So PO4 is our strongest, then CO3, then Cn. Our weakest base is that oxalate ion, C2O4. C2O4, right there. Which of the following is amphiprotic? Which of the following is not amphiprotic? So amphiprotic has to be, has a free hydrogen, a negative ion, or can be water. So here's water. This one has a free hydrogen and a negative ion, a free hydrogen and a negative ion. So it can't be this, it can't be this, and it can't be this. So H3BO4 is our one that is not amphiprotic. This is only an acid. H3BO4 is only an acid. Okay, at a given temperature, a sample of pure water has a pH of 7.1. Which of the following is true? Okay, so a couple of weird things here. First off, it says that it's pure water, so it's neutral. And you're probably wondering why, oh no, the pH is above 7. pH is, so 7 is neutral at 25 degrees Celsius. Once you start changing the temperature scale, the new pH is actually different, okay? So why do we say pH is neutral at 7? It's because I was going to write KW, but so here's water and it turns into H plus and OH minus. And at 25 degrees Celsius, sorry, I should put like some joules here, some energy. So at 25 degrees Celsius, this concentration of H plus, or you could write H3O plus, is 1 times 10 to the minus 7. And this is also 1 times 10 to the minus 7. So if you, this is at 25 degrees Celsius, and if you took the negative log of this number right here, it'll equal 7. If you took the negative log of this one right here, it'll also equal 7. Now, let's say if you increase the temperature makes this thing shift to the right. And if you make it shift to the right, this number will become bigger, okay? It might not become this big, but let's say it does, it becomes, just to make the numbers, the math easy for me, let's become minus 6. That's really, really big. Okay, so now if I took the negative log of that, the H plus concentration would actually be 6. But the OH concentration would also be 6. Okay, and 6 would actually be our new definition of neutral at this really, really high temperature. Okay. But the important thing to understand is that my H plus concentration and my OH concentration is always going to be equal in a sample of pure water. Okay. So is this stuff going to be neutral? Yeah, it's going to be neutral. Okay. So it's going to be neutral, and the pH would equal the POH. Okay. Or the H3O plus or the H plus, and the OH minus will also equal here. So that one right there. This one has the potential of being right if it said equal right there. Okay, but it doesn't, so it's wrong. So that's my answer right there. Which of the following is a definition of pH? pH, this means the potency, or in other words, putting the hydrogen concentration on a logarithmic scale. So it means the log scale of hydrogen, hydrogen ion, which is the same as hydronium, which is H3O plus. So which one of these equations right here puts hydrogen on a logarithmic scale? This one and this one, but since it's a negative log scale, so that's our answer right there. What is the mass of NaOH required? What is the mass of NaOH required to prepare 100 mils of NaOH that has a pH of 13.62? So my first thing is that I don't want to find hydronium. I want to find hydroxide. So I'm going to be using the POH scale. And so the POH scale is 14 minus 13.62. So 14 minus 13.62 equals 0.38. So 0.38 is my POH. Okay, and they conveniently put that there to mess you up, but that's not grams. So my POH is 0.308. Now I want actually my OH concentration, and so I'm going to take the anti-log, or 10 to the minus 0.38, and so my OH minus concentration equals 10 to the minus 0.38, and I get 0.41, 0.4168, and that's molarity. And again, they throw that as an answer there in case you got that far. But that's not it, because we want mass. We're looking for grams. Okay. So what I'm going to do with this number right here is I'm going to times that by, I want moles. So I'm going to go 0.4168, and that's moles per liter, 1 liter. I want liters to go away, so I'm going to times that by the liters that we have, 0.1 liters. Okay, and that cancels out right here. And then I'm going to, now I have moles of NaOH, but I want grams. So sodium is molar mass is 23. This is 16. This is 1. 23 plus 16 plus 17 is 40. So I'm going to be timesing this by 40. This is supposed to be a 40, not 46. 40 grams per mole. So 0.41 times 0.1 times 40 equals 1.6674. Which rounds up to 1.67. So that's my answer for that one. Which of the following hypothetical acids would have the lowest conductivity? Okay, these concentrations are somewhat important, but I kind of can see that they're unimportant because we have Kas that are just like so different. Like, so this Ka is just such a small number that it implies that this acid right here is not going to ionize very well. And since this acid is not ionizing very well, it's it's probably going to be my answer. Like I can guarantee that this one is going to be my answer right here. Okay. If this was close, like if this was also, say, if this said 1 times 10 to the minus 3 and or say if it said like 2.0 times 10 to the minus 3, then maybe we'd have to start looking at some calculations to compare to this one and looking at like an ice table kind of thing or something like that to compare it. But since it's like times 10 to the negative 6, it's just such a small number compared to the other ones. So we can pretty much say that it's going to be that one right there. Number 31, what is the net ionic equation for the hydrolysis of NH4Cl? Cl is a spectator ion because it's coming from strong acid HCl, so that's not going to react with water at all. So hydrolysis is reacting with H2O, so H2O plus NH4. So we know it's going to be either this one right here or this one right here. Now, if we look at our table right here, it actually kind of just tells us this. Let's go look up at NH4. NH4 is right here. It turns into H plus and NH3. NH4 is right here. It turns into H plus or H3O plus and NH3. That's my answer. Okay. What is the approximate pH of 0.1 molar solution of the salt this? This is kind of nice because we just looked at this one. So that's our spectator. We saw that NH4 is an acid. Okay. It's an acid. And more importantly, it's a weak acid. Okay. So it's not going to be this one right here because that's the pH of a strong acid. This one's weak. Okay. It is an acid though. So it's not going to be making neutral and it's not going to be making base. That's my answer. Okay. Consider the following indicator equilibrium. HIN and makes IN its colorless going into blue. What is the effect of adding some acid, HCl, to a blue sample of this indicator? If you add acid into this thing, and this acid is just pure H3O plus, okay, because it 100% ionizes, it'll increase this and it'll make it shift to the left. Okay, so we know that's shifting to the left, but more importantly, it's going to be going from blue and turning the amount of blue will decrease and the colorless will increase. So it'll be less blue. Okay, and that's my answer. And then what do we got here? A whole blank page. Okay, weird. Okay. An indicator has a Ka that's 4 times 10 to the minus 6. Which of the following is true for this indicator? So if I want to find the pKa, or in other words, so if I want to find the pKa of this thing, I will have to take the negative log of this number right here, 4 times 10 to the minus 6. And that'll be my pKa. My pKa is actually going to be where my H indicator is roughly equal to my indicator minus. Okay. Or in other words, the transition point when it's transitioning between two colors. Like say if H indicator was blue and my indicator minus was yellow, my transition point would be green, a mixture of these two colors, and these two concentrations would be roughly equal, and that'll be the pH at when they're roughly equal. And we can find that by finding the pKa. So I'm going to take the negative log, so minus log 4 times 10 to the minus 6, and that goes 5.397. 5.3979, okay, which is 5.4. Okay. So now we need to find which indicator it is. So we're looking at the midpoint has to be 5.4, and our options are methyl red or bromocressyl green. So let's go take a look. Methyl red or bromocressyl green. So here's methyl red, and here's brom green. Okay, so number that we're looking at is a midpoint, a mid number of 5.4. This is not the middle number, right? So in between these two numbers right here, like perfectly in between, is 5.4. So we know that this is our answer. At 5.4, this thing is bromocressyl green is going to be pretty much blue. That's not the midpoint of the transition right here, but 5.4 is right there. So what did I say it was? Methyl red. So 34C. Oxalic acid dihydrate is a pure, stable, crystalline substance. Which of the following describes one of its uses in acid-base titration? Since it's so pure and it's stable, that means we can use it for titrating because we can make a very, very accurate primary standard with this. This is a definition question. I make a very accurate primary standard so that we can use it for titrating and figuring out what are the concentrations of like other bases or something like that. Okay. If you didn't know this answer, what you could do is like, is it a buffer? And be like, no, a buffer is equal parts conjugate acid and base. Did not say that in there. A chemical indicator or a stoichiometric indicator, which is kind of like the same thing. That means like, just like the previous question, that means it changes colors once it is in the presence of something, or it changes colors when it reaches a stoichiometric equivalence point. And the whole description of this oxalic acid does not talk about changing colors at all. So it just can't be this. It's just process of elimination. It has to be a primary standard. What is the net ionic equation that describes the reaction of HCl and PbOH2? So for this one right here is we have this is a monoprotic acid, okay, and we have two OHs right here. And we want the net ionic equation. And I think PbCl is should be low soluble. Just want to double check. I'm like 99% sure. Yeah, PbCl low soluble. So that's going to be forming a precipitate. So this is kind of a tricky question because it's a little bit of chapter 3, chapter 4 in there. And PbOH2 is solid right here. So we have to write that. So it's going to be forming so it has to be net ionic. HCl, once it's placed in water, it's completely ionized and turns into H plus and Cl minus. So it cannot be this one right here. It says HCl together. PbOH and PbCl are forming precipitates, so it can't be that one right here. It's more than just H plus and OH reacting. And again, PbOH and PbCl, these ones aren't forming precipitates like they should be. And PbCl2 does form a precipitate. The acid breaks up the hydroxide, but then the lead combines with the chlorine right here to form this precipitate. This is my answer right here. Which of the following would be used to prepare an acidic buffer? So an acidic buffer is conjugate acid, conjugate base pair. So the conjugate base of HF is F minus. That can't be it. H2S and HS, Na is a spectator. these ones are conjugates. NH3, NH4,